In this video, we're going to be looking at electrochemical cells, specifically how electrochemical cells are made, how we can increase the output voltage from an electrochemical cell, and how to interpret data to work out voltages that they're going to induce. The first task that I want us to think about, though, is how to complete half equations, because this is going to become really important when we look at the details of how electrochemical cells work. So pause the video, have a go at the 5 questions on the screen, and then we'll go through answers shortly. Hopefully that's enough time for you to have completed those questions, so we'll just go through them quickly now. So zinc 2+ becomes neutral discharged zinc. To do that, we need to add 2 electrons to it. Exactly the same thing for copper. Currently it's 2 positive. We need to add 2 negative electrons to make it neutral. Oxygen is going to discharge to become O2, which is diatomic. That means that we're going to be losing 2 electrons. However, we have got to have 2 of those oxygens in the first place, because it's diatomic, which means we lose 4 electrons in total. Chlorine is diatomic, and each chlorine has lost an electron, so therefore that's going to be 2Cl-. And to make neutral aluminium, you add 3 electrons to it, which means that aluminium must have had a 3 positive charge. We're going to be thinking about how metals are able to induce a voltage when they're put together in an electrochemical cell. To do that, we're going to start thinking about magnesium as an example of a metal. So what I'd like you to do is just quickly sketch the electron structure of magnesium and have a think about what do metals tend to do, particularly what do they tend to do when they react. And the answer to that is they lose their outer shell of electrons. And the reason they lose an outer shell of electrons is to make sure that they've got a full outer shell, or a noble gas electron configuration, a full outer energy level. That makes them more stable. So all metals tend to lose electrons. They tend to undergo oxidation and then become a positively charged ion, as magnesium has. Now, what we can use this information to tell us about is the reactivity of the metal. If a metal is more reactive, it means it's got a greater tendency to lose electrons. Metals that are less reactive find it harder to lose their electrons. So a more reactive metal will lose electrons more easily than a less reactive metal. And we can use this bit of information to generate electricity, which is what we're going to be looking at next. So we're going to try and create a voltage between 2 bits of metal. The 2 bits of metal that I've chosen are magnesium and copper. The reason why I've picked those 2 metals is there's quite a big difference in the reactivity between them. Magnesium is quite high on the reactivity series and copper quite low. So because of that, I'm able to create an electric potential, or a voltage, between them. Both metals want to lose electrons. However, magnesium is able to lose electrons more readily, more easily. The other way that we can work that is that magnesium has a greater tendency to undergo oxidation. A greater tendency means it's more likely to happen, it's more easy to do, and oxidation means lose electrons. So what we're able to do with these 2 metals, if we put them in the right circumstance, in the right situation, we're able to get magnesium to lose electrons and copper to absorb and take in electrons. The copper isn't going to want to do that forever, so eventually those electrons are going to need to go somewhere else. But for the purpose of understanding what's going on here, we can make magnesium lose and copper accept the electrons. And that movement of electrons creates an electric potential, a voltage between the magnesium and the copper. So in effect, what we've done is create an electrical current. We've created a power source, and we can use that power source to generate electricity and to make circuits work. So we're going to have a go at doing this. We're going to take 2 pieces of metal. We're going to take a beaker of salt solution, which is needed to complete the circuit. And we're going to take a voltmeter, as you can see in the diagram on the screen. We're going to connect a range of different metals in different orientations to that voltmeter to see what kind of voltage we can create with the different metals. So I'm going to take my beaker, 100 millilitres of salt solution in it, and then you can see in the table on the screen the different metals that I'm going to connect in that orientation. So I'm going to swap the metals over. You can see for the first test I'm going to do magnesium on electrode 1, then zinc, then I'm going to flip those over, and then I'm going to do the same thing with magnesium and copper, and then finally zinc and copper. It would be really useful if you could draw the table ready to record the results of the practical. So I'm going to have a go at inducing a potential difference, creating a flow of electrons with just some pieces of metal and some salt solution. So what I have in this beaker is some salt dissolved in water. I've got a selection of different metals, so everything from aluminium to magnesium to copper, and we're going to test some different metals in combination with each other. And to measure the voltage that's induced, I've got a multimeter. The voltage I'm going to create is going to be quite small, so I'm not going to be able to power anything like a light bulb with it, so I'm just going to use a multimeter to measure the voltage that's created. So the first two metals that I'm going to test are magnesium and zinc. You can see that I've connected them to my multimeter, and I've got a beaker with my salt solution in, ready to add the two metals to. So I connect my electrode with zinc and my electrode with magnesium, making sure that those metals do not touch. And then you can see that a voltage is induced, and we'll just wait for that to stabilise. So 0.72. The next test I'm going to do involves swapping the two metals over. So I'm going to take the zinc off one electrode and reconnect the magnesium to it, and then attach the zinc this way round. And then I add those to my beaker again. And you can see this time the voltage induced is minus 0.71 or minus 0.72. That means that the current is flowing in the opposite direction. The induced potential is in the reverse polarity, the reverse direction, because I've connected the metals in the opposite way round. The next two metals that I'm going to test are magnesium on my first electrode and copper on the second. So when I add those two to the beaker, you can see that a voltage is induced, and this time the voltage is much greater. So we'll just let that stabilise at 1.51 volts. The next test I'm going to do involves swapping the two metals over. So I'm going to put my magnesium on the second electrode and copper on the first. And you might be able to make a prediction about what happens for these two metals. So I add them to my beaker of salt solution, and this time you can see that the voltage is minus 1.5. So we're going to have a go at analysing the data that we've collected. You can see that we tested two combinations of metals in different orientations. What I want us to think about is what affects the size of the voltage and what affects the direction, the plus, negative, the polarity of the voltage. So for the two types of metals that we've tested, we've got firstly a positive and negative result for each one. And that depends on where the most reactive metal is. If the most reactive metal, for instance in this first test, that's magnesium, if the most reactive metal is on electrode 1, then the voltage is positive. And if the most reactive metal is on electrode number 2, then the voltage induced is negative. And that's because the most reactive metal is the one that's got the greatest tendency to lose electrons. So it's losing electrons and sending them to the least reactive metal. And if you swap the metals over, that means the electrons are going to be flowing in the reverse direction. The other thing we need to consider is what affects the size of the voltage induced. The size of the voltage that we create, the magnitude of it, is determined by the difference in reactivity between the two metals. Magnesium and zinc are relatively close together on the reactivity series, well, relatively close compared to magnesium and copper. There's a much greater difference between the reactivity of magnesium and copper, therefore the voltage that's created, 1.51 volts, is much greater. So bigger gap in reactivity means higher voltage. And then if you swap the metals over, that changes the direction that the electrons are going to flow in. So there's two questions on the screen in the orange box that I'd like to have a go answering. What conclusions can we make from the data about the reactivity of the metals, about which electrode they're connected to, and what might affect the voltage produced? Pause the video, have a go at those questions. If you want to rewind a bit, please feel free. The next thing that we are going to consider is how can I predict the voltage that's created for zinc and copper. The first thing that I can probably do is work out which way round is going to give me a positive result and which way round is going to give me a negative result. So I want you to have a little bit of a think. Again, you can pause the video if needed. For zinc on electrode 1 and copper on electrode 2, is the result going to be positive or is it going to be negative? And then think about the same thing for copper and zinc the other way round. Which one will be positive, which one negative? Pause the video, have a think. As we said before, where the most reactive metal is on electrode 1, that means that you are going to have a positive voltage or positive potential difference. Where the most reactive metal is on electrode 2, that becomes a negative voltage. And zinc is definitely the more reactive metal of the two. That's something that I would expect us to know. So that means when the most reactive metal is on electrode 1, it's a positive result. And when it's on electrode 2, it's a negative result. So we've kind of worked out the direction of the voltage. What we now need to do is work out the size of the voltage. And to do that, you're going to need to consider the other data in the table. And it is definitely possible for you to work out the magnitude of the voltage that's created. So I want you to pause the video and see if you can work out how you might go about doing that, just using the data that's in the table above. So when you look at the data in the table above, you can see that we've tested zinc and copper before. So zinc was tested in the first tests that we did, and copper was tested in the second set of tests. So if I can work out the difference between the voltage in the first tests and the difference to the second test, so if I can work out the difference between those voltages, then I can kind of work out the voltage that zinc and copper are going to induce. So the difference between these two, I'll do the largest take away the smallest, 1.51 take away 0.72, that gets a voltage of 0.79. So when I use zinc and copper, the size and magnitude of the voltage is going to be 0.79. Even though I've not tested that yet, I can work that out by using the voltages in the table. And then I've already worked out which is going to be positive. So I know zinc and copper is going to be 0.79 positive because zinc is on electrode 1. And when the most reactive metal is on electrode 2, it's going to be negative. Okay. So hopefully you managed to work out how we might go about doing that. And we're going to have a go at a few practice questions to be able to do that shortly. So the next thing we're going to do is think about, well, how on earth does this work? How can we create a voltage from just 2 bits of metal and some salty water? And we're going to use a different example. We're going to use zinc and copper, the one that we've just been talking about. So because the electrodes are made of 2 different metals and there's a difference in reactivity between those 2 different metals, we're able to make electrons move through a circuit. In this example, the zinc is the most reactive metal, copper is the least reactive metal. Therefore, zinc has got a greater tendency to undergo oxidation. That means it's more likely to lose electrons. Therefore, it gives its electrons up more easily, and those electrodes then transfer through the circuit over to the copper. Therefore, the less reactive metal, because it forms ions less easily, it loses electrons in a harder way. It's not as easy for it to lose electrons. Therefore, that receives the electrons and becomes the cathode. You'll notice that there is a slight difference between electrolysis and electrochemical cells in the way we label the 2 electrodes. In this case, the zinc, the most reactive metal, is the anode, and the least reactive metal is the cathode. The anode is negative in this example, If you were to think back to electrolysis, the anode is actually positive in electrolysis. So this is the other way around. The anode is negative and the cathode is positive. So in effect, what's happening here is the more reactive metal is forcing the less reactive metal to accept electrons. And by doing that, we create a circuit that electrons can flow through. We're going to have a look at this in a little bit more detail now, though. So what I've drawn on the screen for you is two metals. In this case, I'm going to use magnesium and copper because they've got a really big gap in reactivity between them in my beaker with my salt solution in it. And I know that electrons are going to flow from the most reactive metal to the least reactive metal. So you're going to need to draw this nice and big in your book with enough space to kind of annotate and draw some extra things. And we're going to look at the detail of exactly how this works. This is definitely one of the hardest topics that we're going to be looking at in GCSE chemistry. So I'm going to go through it relatively slowly. If you need to pause, rewind the video at any point, again, please feel free to do that. What you might also want to add into your diagram, which I haven't done just to make it a little bit simpler, is the voltmeter, which is going to sit in the circuit between the magnesium and the copper. So we've already thought about which direction the electrons are going to flow in. They go from the most reactive metal to the least reactive metal. So in this case, that's from the magnesium to the copper. To allow the electrons to do that, magnesium needs to turn into an ion. So it undergoes oxidation, it loses electrons. Those electrons leave the magnesium and the magnesium ions dissipate into the solution or diffuse into the solution. So over time, what you would see is that magnesium electrode becoming smaller and smaller as the magnesium ionizes and goes into solution with the salt. Those electrons that are released from the magnesium, because it's undergone oxidation, are now going to go through the circuit. So they travel round through the circuit, through the voltmeter, and that's where my potential difference comes from. Now, copper does not really want to have these extra electrons in it. So they're not going to stay and build up like a big bank of electrons in the copper. The electrons are going to go somewhere else. And the place they're going to go is into the solution. And this is why you need the salt solution in the first place. If I just have some magnesium and copper and connect them with a piece of wire, nothing happens. When I put them in the salt solution, as you saw in the video, that's when the electric potential is created. Now the salt solution, I'm just going to label those first. So the magnesium is the negative electrode because that's where the oxidation is happening, and copper is the positive electrode, which you might think is a little bit counterintuitive. So we call those the anode and the cathode. In the salt solution, this time I've used sodium chloride, I've got sodium ions and hydrogen ions. And we're going to be moving the electrons from the copper into one of those ions. And we're going to think about which ion it might be. And the kind of rule is really similar to the rule for electrolysis. If I've got a metal that's more reactive than hydrogen, then it's going to be hydrogen, because otherwise we're going to be discharging sodium and that's just going to react and displace hydrogen anyway. So which ion are the electrons going to go to and which is going to discharge, which is going to form? The answer to that is hydrogen. So electrons move from the copper into the hydrogen that's in solution. However, hydrogen is diatomic, so I'm going to need 2 ions of hydrogen for 2 electrons to be moved into, and that then becomes normal neutral hydrogen, and that can be seen given off as bubbles from that electrode. So the copper electrode in this case is not going to change size, it's not going to get smaller because it's not being kind of corroded, it's not ionizing. But what is instead going to happen around that electrode is hydrogen will form, and you'll see bubbles of gas being given off. What we also need to be able to do is write some half equations for what's happening at each electrode. So we'll start with the magnesium side. So we begin with Mg2, just normal magnesium, sorry, and it turns into Mg2+. When it does that, it oxidizes, so it loses electrons, and those electrons are then separate to the magnesium. So that half equation represents the oxidation, the loss of the electrons from the magnesium to now being in the circuit. On the other side of the cell, those electrons that are then received by the copper don't stay in the copper, they move to one of the ions in the solution, and that ion is hydrogen. So I start with a H plus ion. It gains an electron to become hydrogen. However, hydrogen is diatomic, so that's H2, which means I need two H plus ions to start with, which means I need two electrons to be gained by them. So you need to be able to kind of use some ionic equations to explain what is happening. What I'd like you to make sure that you've done now is that you've got an annotated diagram of this with all of the different extra details that we've talked about. The next thing we're going to think about are some factors that affect the size of the voltage, the magnitude of the voltage that's induced. So the first of those factors is that the metals we use, if they are further apart on the reactivity series, so if there's a bigger gap between them, then you get a higher voltage induced. If they're very close together on the reactivity series, the voltage induced is much smaller. The second thing that is going to affect the voltage is the electrolyte. Now the word electrolyte is just a scientific term for the salt solution that we put the electrodes into. So depending on what chemical we dissolve in the water, that's going to affect the voltage that is created because the metals are going to react with different ions in solution. The third factor is that the flow, the direction of the voltage, which is a factor that affects it, is determined by the position of the metals on the electrodes. So if I have the more reactive metal on the first electrode, it might be positive, and if I swap those over, then it becomes negative. So the direction of the flow is affected by the position of the electrodes, or the metals that are the electrodes. And the fourth factor is that you can increase the voltage that's produced by connecting lots of these cells, or electrochemical cells to give them their full name, in series. And by connecting them all up in a big long line, you're then going to create a much bigger voltage. So here's a little diagram just to represent that. What you need to be really careful to do when you connect them is to properly connect them in series. So you can see here my first cell, the negative electrode of it is connected to the positive electrode of the next cell, and so on. So the negative connecting to the positive, and so on, so that all of the cells are acting in the same direction, so the voltage builds up. If I put one of the cells in the wrong way round, that would kind of cancel out some of the voltage, and that would bring the voltage down, or potentially stop the voltage being induced at all, or potentially reverse the direction. So those are the four factors that can affect the voltage of an electrochemical cell. So pause the video and make sure you've got those written down. So we're going to have a go at some questions. As you can see on the screen, there is a table of data. We've got electrode A being zinc in both cases, and electrode B either being tin or copper. And you can see the voltages that are induced in both cases. We're told if metal A is less reactive than B, then the voltage is positive. And if B is the least reactive, then it's going to be negative. So in both cases, you can see the voltage is negative. That gives you a clue as to which is the most reactive metal and which is the least reactive metal. What I then want you to do is have a go at the questions in the yellow box. So they say which of the three metals is the most reactive, which out of the three is the least reactive, so put them in order basically of reactivity, and then you've got two things to work out. So I want you to calculate the voltage of a cell with a positive or negative sign, formed where tin is electrode A and copper is B, and then I want you to calculate the voltage with those two the other way around. So pause the video and have a go at those questions. So hopefully that's enough time. If you haven't paused it, do that quickly. We're going to go through the answers to those questions. So which of the three is the most reactive? Well, we know from the table of data that these voltages are negative. Therefore, metal B is the least reactive in all of these cases. So where the voltage is negative, metal B is less reactive. So from that I can work out pretty straightforwardly that zinc has to be more reactive than tin and copper. So the order of reactivity definitely starts with zinc. I then need to work out which is the least reactive. And the bit of information I use to do that is the biggest voltage, so the voltage with the greatest size, is created when you've got the biggest gap in reactivity. So zinc and copper have got the biggest voltage in terms of its magnitude, therefore they've got the biggest gap in reactivity. So copper must be the least reactive, and therefore tin goes in between the two. The next thing we've got to do is work out the voltage formed where tin is on electrode A and copper is on electrode B. Well, I'll do positives and negatives first. Tin is more reactive. So if tin, the more reactive thing, is on A and the less reactive thing is on B, that means my voltage is going to be negative. And to work out the magnitude, I find the difference between the two voltages in the table, which is 0.1. So that first calculation is minus 0.10. I'll use the same number of decimal places as the question. And then the second one, I've swapped those two things around. So the least reactive thing is now on A. So copper is now on A. Metal A is less reactive than metal B, therefore it's positive. And the size, the magnitude, will still be the same, 0.1. The last thing that you're going to have a go at doing today is some questions about electrochemical cells. So they're uploaded to show my homework. I want you to work through those, and then at the start of next lesson, we'll go through the answers to them. So thank you very much for watching. Remember, if you need to go back, if you don't understand any of this, please watch it again, just to make sure that you've got your head around it. We'll go through the answers to the questions next lesson. Thank you for watching. Bye-bye.